Thank you very much. So I would like to start by, well, apologizing for not being there. I really would have liked to come, but there were several medical issues that were holding me back. In fact, for the last 2.5 weeks, I've been taking a lot of pain medication because of a serious lower back problem. So if I'm a little bit groggy, then, well, please forgive me for that. Let's see. Try and share my screen. Did that work? Yeah, can you see my title screen? So today, well, I'm going to have a light talk. It won't be very heavy, and it's joint work with Pablo Ferrari. I think most of you will know him. So when you work at a university for a longer time, at some stage they put that clause in you, and you have to do some administrative duties. And this also holds for me. I've been the director of our institute for the last couple of years, and that really eats away at your research time. So I was very happy when Pablo invited me to join him in Buenos Aires for a week this year. And I went there and, well, we just worked, basically. We had a nice problem, we thought about it, and that's what I'm going to talk to you about. So it's about periodic conic growth model, and we will show that it's solvable in a certain sense. Now let me start by reminding you of the Hammersley process. And what you see here is a sample of paths of the Hammersley process. Let me try and remind you what this is. If you look at the horizontal line over here, it crosses the paths, and these crossings, they could be seen as locations of particles. So these are the Hammersley particles, and these particles, they just stay in place until when you go up in time, you meet a Poisson process, one of the red points, and then the closest particle to the right jumps to the left and then stays there. So all particles are moving to the left, and they form these paths, and this can be defined on the whole of R2. Now, you see here a sample of the stationary version of the Hammersley process. And that means that if you look at the horizontal line, the locations of the particles form a Poisson process, in this case with intensity 1. And also the Poisson process in the plane has intensity 1. And then there are some more things that we know. For example, if you take the vertical line here, you look at the crossings with the path there, that also forms a Poisson process, which is with intensity 1. And this Poisson process on this part is actually independent of the Poisson process of that part. So this is all nice and a little bit classic. And well, I'm happy to say that Pablo and I did some work on this also in our earlier years. Now, what I'm going to do now is I'm going to rotate this picture. Could you confirm that you actually see my mouse when I'm moving it?
Yes, we can hear you. And we can see the mouse.
The mouse, excellent, that's good. So this is the same picture, except it's rotated 45 degrees. And here the name corner growth process comes from. I'm not quite happy with it. Maybe I should change it. Maybe one of you has a suggestion for the name later on. But so now what happens is that, well, all the paths, they're now a little bit like horizontal, and they have minima and they have maxima like this. And the minima correspond to the Poisson process. And from such a Poisson process, a corner starts growing like this. And if you draw in this picture a horizontal line, you again get crossings with the blue paths. But now the crossings consist of two different types. So you have a crossing with a positive slant, which you call a positive particle. And then you have crossing with a negative slant, which we call a negative particle. And this process of particles can also be seen as a Markov process. And as we move up in time, so we go up a little bit, what happens is that the positive particles, they just move to the right at unit speed. And the negative particles, they move to the left at unit speed. And then sometimes, for example, here, a positive and a negative, they meet, and then they annihilate each other. So then they're gone. And sometimes you encounter a Poisson process. And this is like the birth of a positive and negative particle moving in different directions. So that's like this. So these horizontal lines, the particles on this on these lines, they also form a process. And well, just for convenience sake, I call also that the corner growth process on this line. Now you can show that in this stationary case, and I don't have a reference, I'm not sure if it's written down anywhere, but it is true. So in the stationary case, when you take the crossing with a horizontal line, the negative particles and the positive particles, they both form a Poisson process. I think both with intensity 1/2 square root 2. And they're independent of each other, these two processes. So that's what you can show. And okay, that's interesting. And now, when you define, these moving particles, positive and negative particles, then you can consider this on a periodic version, on a circle. And when I visited Pablo, he came up with this problem. In fact, he had some other motivation for this, that he was looking at some discrete thing, and then when you scale this discrete version in a certain way, you actually get these moving particles, plus and minus. And then we thought of the link with the Hammersley process, and we tried to prove something for this process. So the state space is, well, you have the circle, 0L. So you in this entire talk, you have to remember that 0L is a circle, so it's actually periodic. So when you move to the right here, you enter to the left here. That's important. And you can either have 0 particles, so that's the empty configuration, or you can have n positive and n negative particles. So we enforce the fact that the number of positive and negative particles are the same. This is relevant. You can deviate from this, but you get a different process with different properties. But in our case, we will enforce that the number of positive and negative particles are the same. And then you get a state space like this. Okay. And then, so these particles, well, let's go back one thing. So these particles, the positive particles, they move to the right, the negative particles move to the left. They can meet each other and then they annihilate. And what can happen is that a new particles pair is started at some place, consisting of a positive particle to the moving to the right and a negative one moving to the left. That's the way this Markov process moves. Now, when you look at a fixed time, then you can make the following observation. Suppose you have this positive particle here, so it moves to the right, it will encounter one of the negative particles at some stage. It might encounter a new pair of particles created by Poisson process, but then, that negative particle cancels, and then there's a new positive particle, and that's still linked to the particle we started with. So this particle will encounter one of the negative particles here, but, well, first you see to the right is a positive particle, and then a negative particle. So these two, they will meet up in the end. Maybe interfered by some new pair that's created, but still, the path of this particle and the path of this particle are linked together. So they cancel each other. And then you get two new positive particles, and then again a negative. So these one cancels each other as well. So this blue one actually is also linked to this negative one. So that's why they're all blue, all three. And this one will connect to that one. So these 4 particles, they belong to the same path. And then in the end, you get a red one again, which is linked to this red one. And since there are the same number of positive and negative particles, the path of the particles, they will all link up and they will be closed. It will be a closed path. So these paths, they will form rings inside the cylinder, where the cylinder consists of the circle 0L and then time going from minus infinity to plus infinity. And here's a sample of this. So here's the cylinder. We start at 0 with an empty configuration. On the black points, new particle pairs are created. And you get all these rings that when you follow the path of a particle, you get a closed ring. And when you take a horizontal line here, the crossings, they form the actual configuration of the periodic corner growth model. We will see this picture several times because there's some interesting questions that you can ask about this picture. Okay. Now, the first order of business is, of course, to see, is there a stationary measure? Well, there is. That's kind of obvious. But what is the stationary measure for this periodic corner growth model? So we start with a dominating measure on this state space E. Dominating measure being, well, it's just a Lebesgue measure. And then we scale it in such a way that each part of the state space, so the empty configuration with 2 particles, 4 particles, 6 particles, etc., each part with n positive particles has total mass 1. So that's the dominating measure on this E. And this is a slight abuse of notation, but I think it's clear what it means. And we're trying to find a stationary measure which is dominated by this one. Now, I told you before that if you look at the Hammersley process, this kind of turned around Hammersley process, and you look at the entire line, then the positive and negative particles, they formed independent Poisson processes. And in our case, well, we have a finite set, finite length, and we know that there are the same number of positive as negative particles. So Pablo is not a scared guy, so he thought, well, maybe it's obvious that the number of particles in the stationary version must be kind of Poisson, but since you have the same number for positive and negative, we just condition the two things to be equal. So you take independent Poisson with parameter lambda, and then you condition on the fact that they're equal, then you get a new distribution, of course, for this number, which is denoted here by P of lambda. And well, we were not sure if this has a name already, but we just called it Poisson-squared because the probabilities are the squares of the Poisson probabilities, and then of course normalized by some normalizing constant. So our guess would be that you want to have a stationary measure, you take a draw from this Poisson-squared distribution with some parameter lambda, and then you distribute the positive and negative particles just uniformly on this 0L. That's the idea. Oh. And that turned out to be true for the correct choice of lambda. So that's a good starting point. It's always good if your lucky guess turns out to be true. So here's a theorem that the stationary measure for a periodic corner growth model is just given by this dominating measure times P lambda of n. And of course, since the sum of the P lambda n is 1, this is exactly a probability measure. So it tells you what the probability is to have n positive particles, and then you just distribute the n positive and the n negative particles independently of each other in a uniform way. And the correct choice of lambda is L over square root 2, it turns out. So how am I going to prove this? Well, a natural way to do this is by considering the generator of this Markov process. It turns out that's actually quite technical and not so easy. And the reason is that the generator should reflect that the positive and negative particles, they can collide and then get annihilated. And it's a little bit subtle because usually the generator, you condition on a certain configuration, and then you see what happens after time h. Now, if you condition on a certain configuration, then for very small time h, there will be no annihilation. So you will not see the annihilation. So if you just write down the generator like that, without taking into account this annihilation, you actually get the wrong process. You get the process where the number of particles is growing all the time. And that's not what you want. So you need to somehow make sure that your generator contains the part where you get annihilation. And for this, you need to do some technical construction. And it's not so easy. So I will not do that in this talk. In fact, I will do a different method, which you can, it's a little bit informal, but you can make it into a formal proof. So what I will do is the following. I will take a configuration distributed according to our so-called stationary measure, mu, and then we consider the configuration after time h, and we're just going to write up what is the probability density of the possible configuration of this x of h. And if this is the same as mu up to small order of h, then mu must be the stationary measure. So how does this work? Well, we can first start by considering the probability that after time h you have an empty configuration. And there are two ways that this can happen. The first way is, well, you just start with an empty configuration and it stays the same. It stays empty for this time h. And the probability of that happening is 1 minus the probability that you encounter a Poisson process, which is h times L. So this is one way to get the correct distribution, the correct configuration. And the second way is that you actually start with two particles at time 0, but they annihilate each other within this short time interval. And then when they annihilate each other, you end up with the empty configuration. So we start with one particle, has probability p lambda of 1. And then these two particles, well, the positive particle can be wherever, but the negative particles should be within size 2h of each other. And since positive is moving to the right at unit speed and negative to the left, within time h, they can bridge this distance 2h and they will be annihilated. So the probability of finding the negative particle within 2h of the positive one is 2h over L. So that's this one. And all the other effects are smaller order. And then you add them up and you realize that p lambda of 1 is actually lambda squared bigger than p lambda of 0. Lambda squared equals L over 2, and you get exactly, L squared over 2, and you get h times L here cancelled with this one, and you end up with this value, which is the correct value, right? It's the same value as you would have for mu. Now, take a different configuration, the idea is the same. So you want to have a configuration with n positive and n negative particles at some specific location. So how do we do this? Well, you start with a configuration in the right positions. So in position x1 minus h, x2 minus h, etc. And y1 plus h, because the negative particles move to the left. So y1 plus h, y2 plus h, etc. You start with that and you make sure there's no Poisson probability, no Poisson point in the interval 0h. So that's this factor here. That's one way. And the other way is, well, you start with two particles too much. So with n plus 1 positive particles and n plus 1 negative particles. It has this probability. And then what happens? What should you do? Well, I take these n plus 1 particles. I put the first one at x1, the second one at x2, etc. And then the last one, I link with the last negative particle. So what you end up with then is dx1 over L, dx2 over L, dy1 over L, dy2 over L, etc., which is this factor here. And then the last two particles, well, one can be wherever, and the other one has to be within range 2h. So you get this factor 2h over L. Now, of course, I put the first one in the first place, second one in the second place, etc. I can do this whichever way I like. So I can permute the x particles, I can permute the plus particles, I can permute the negative particles, and you get this extra factor n plus 1 factorial squared, which of course helps us a lot because it cancels the one that's present in the p lambda n plus 1, right? Because p lambda n plus 1 is lambda to the 2n divided by n plus 1 factorial squared times normalizing constant, which is irrelevant. Okay, so what happens is if you calculate this, it turns out it's exactly, again, h times L, just like in the case with the empty configuration. It cancels and you get order h, like this. So this proves that after time h, the distribution, in fact, is the same as it was in 0, and therefore you get a stationary measure mu. This is very nice. We have this stationary measure, and well, let's see what else we can find. So I look at this picture again. Here's a realization of the process that we're interested in. And somewhere at the top, we are nearing the stationary version. Now, I'm sure maybe you cannot see it, but maybe if I enlarge a little bit, there are these black points, which are the Poisson points, and then of course there are the green points, which are the maxima of the paths. That's where a positive and a negative particle annihilate. And those of you who have seen maybe the Hammersley process or some other interacting particle process, you know, what we would like, of course, is that these green points, they also form a Poisson process. That would be natural if that's the case. And in fact, we want a little bit more than that. Let's see. What we want is a type of reversibility. Reversibility meaning that if we look backwards in time, then these green points, they actually form the Poisson points for the backwards process. So you would like them to be Poisson process, but also you would like them to be independent of the times above. Just like in the original process, the Poisson process above is independent of the configuration at the time that you consider it. So here's a theorem that we can use for that. So the statement is that if you look at a realization of the stationary version from 0 to t, and then you look at the dual points, then these dual points form a Poisson process, and the Poisson process is independent of x of t, so at the top part. So that means that you can go down and you will encounter an independent Poisson process, and that's how you can make the reverse process. And the proof is very similar to what we did before. At least this kind of heuristic proof, almost. All right, so what I'm going to do is I'm going to start at the top, then I'm going to go down, and I'm asking myself, what is the probability of encountering a green point, a dual point? And then I hope that this is independent of the process I started with at time t. So I start with the empty configuration as an example. So I condition on the fact that the empty configuration is, the configuration at time t is empty. And then I look at the probability that there is a dual point in some little interval AB, and in time t minus h up to t. So what has to happen? How can we get a dual point? Well, I have to start with one positive particle at time t minus h and one negative particle, and these two particles have to annihilate. And when they annihilate, you end up with a dual point and also with the empty set at time t, which is what we need. So you get p lambda 1, probability of having two particles, a plus and a minus. I divide by p lambda 0 because of the conditioning. So that's this one. And then what has to happen is that the positive particle has to be in this interval AB, and the negative particle has to be no more than 2h away from it. Right? And this product gives you the right probability, and you work it out, and you get b minus a times h, which is exactly the probability of a Poisson process of finding a dual point there. So that's nice. So when you condition on the empty set, it's correct. Now, just as before, I will condition on some arbitrary configuration at time t, and I will wonder what is the conditional probability that there's a dual point between t minus h and t. And you get the same argument. You need n plus 1 positive particles. One positive particle has to be annihilated by a negative particle, and the other ones, they have to end up in the correct position, this position z. So you get the same factor as we had before. So this p lambda n plus 1, you get the permuting them around, n plus 1 factorial squared. You get the L to the minus 2n, which is positioning the points at x1 to xn, y1 to yn. And then you get the same one as we had before. One positive particle has to be within b minus h, and the other one within 2h of it. And you divide by the density of this conditioning, which is this value. Then you work it out, and you see that the factorials, they get cancelled by the p lambdas. You end up with a lambda to the power n plus 1 2 times n plus 1, and here lambda to the power 2n, so that's a lambda squared. The lambda squared is L squared over 2, and indeed you get b minus a times h. So that's, again, it's the Poisson probability, and what you've also shown that's independent of the condition on xt, which means that the existence of the green point is independent of the configuration at time t, which is exactly what we want to prove. And so this shows that the whole process is reversible. It's like, I want to say Kirchhoff theorem, and I think that's the wrong word. Well, for the Hammersley process, we have a similar theorem. You can go up or you can go down, and the whole thing is reversible. Okay, that's nice. So this is a nice process, and we have a lot of properties. Now, we have this squared Poisson process, and I want to do some trivial calculations for that because it's insightful, turns out. So if we look at the modified Bessel function of the first kind, which is this strange function here, it turns out that for alpha is 0, alpha is -1, alpha is -2, you get relevant values for this Poisson-squared distribution. Yeah, because the gamma is also a factorial, so you get the factorial squared, and here you get lambda to the 2n, or this should be an n instead of an m, my apologies. So you get something with this Poisson-squared distribution. So it turns out that the normalizing constant is I0 in 2 lambda, and you can calculate the expectation and the expectation of w times w minus 1 in terms of I minus 1 and I minus 2. Okay, so that's nice. But then there's a recurrence relation for this modified Bessel functions. And the recurrence relation that's relevant for us is down here. And if you fill this in this formula, you get the following little bit remarkable fact, that the square, expectation of the square of the Poisson-square distribution equals lambda squared. So no modified Bessel functions there, it's just lambda squared. And if you think back of the Poisson distribution, what it says here is that you have Poisson, you have an x and a y independent, both Poisson lambda, and then it says here that the expectation of x times y given x equals y is in fact equal to the expectation of x times y. So the conditioning doesn't make a difference. That's not standard. It's, it's a particular property of the Poisson process, and I cannot prove it in some simple way. I need these Bessel functions for that. Maybe one of you can find some elegant way to prove this. Yeah, so the expectation of x times y given x equals y equals expectation of x times y for a Poisson distribution. Now, this is relevant. It will turn out later why this formula has some relevance. I go back to the sample. I know a little bit now about crossing with the horizontal line, know the distribution. I know about the green points, so that's also nice. What I want to know is more about these rings. These rings are the interesting object here, right, in this picture. What do these rings look like? How many minima do these rings have? Questions like that. And it turned out that one thing that we can say relatively easily is we can say something about the number of rings. So if you go to 0 to t, how many rings do you expect to see? And for those of you who remember this kind of turned Hammersley process, the number of rings is like the flux along the diagonal of the Hammersley process. So that is an interesting thing. You got these Tracy-Widom distributions and the cube root, those kind of things. That's what happens if you look in a horizontal line. A vertical line. Now, don't get me wrong, there's no cube root or Tracy-Widom in this thing because it's finite, so it's a renewal process and you just get normal distributions. But if you have exact formulas and you take the limit from L to infinity, you should get some interesting things there. Anyway, number of rings. What can we say about that? Well, we can calculate the expected number of rings. So how do we do this? So consider a vertical line piece, let's say through the point 0 and from t to t plus h. So it's a small vertical time piece. And my question is, how many rings do I expect to cross this small timepiece? So look at the picture below. Here's time t, here's time t plus h. This is the vertical line. When do I get a crossing through this part? Well, it happens when there's a positive particle here, or when there's a negative particle here. This negative particle will move to the left, and the positive particle will move to the right, and you get a crossing through this line. Okay, so, but I know what the distribution is of at time t because I'm in the stationary version, right? So what is the expected number of rings, of positive particles in this little interval? It has length h, this interval. Okay, well, it's h divided by L times the expected number of positive particles, which is the expected number of expectation of W. Right? That would be the number of positive particles. So if you multiply by 2, you get the number of positive and negative particles. So in time h, you expect 2h expectation W over t number of rings. But of course, we are in stationary version. So in time t, you expect 2 times t times this expectation divided by L. And you can write this in terms of these Bessel function if you like. So we know what is the expected number of particles, of rings. And it's kind of interesting because what happens if L is, for example, very, very big? Well, if L is big, then this ratio goes to 1, this thing, and you would expect square root of 2 times t, number of rings. So the dependence on L kind of disappears, which makes sense because you make the ring wider, but the number of paths doesn't grow from that, or not a lot of it. Right? As L gets bigger and bigger. So it becomes linear in T, this number of paths, and the square root of 2 exactly corresponds to the Hammersley process, because what happens in the Hammersley process is if you have 0L, 0L in the Hammersley process, then the diagonal, the length of the diagonal is square root times L. So T becomes square root times L, you get 2 times L, and this factor 2, that's Coulomb's constant, that's exactly the thing you get in the Hammersley process. So that's also nice, that it corresponds. For small L is also kind of interesting what happens there. If L is very, very small, it turns out that for small lambda, the expected value of W just becomes lambda. Is that right? No, it's 1 over lambda. The expected value becomes 1 over lambda. And then you get 2 over L squared here. So for small L, you get very few rings in this thing. Yeah, I'm making a mistake. For small L, it should be 1, I think. Well, it doesn't matter. When the ring is very small, it's quite obvious what happens. When it's very small, you get very few Poisson points, and one Poisson point immediately forms a ring with itself. Because, you know, it's a very small ring, so it closes the loop very quickly. So you just get rings at each Poisson point, and that determines the number of Poisson points. So it's a trivial case. Okay, so I have a formula for the expected number of rings. That's nice. I can do something else with this expected number of rings. Because if you look at this picture, so I know now how many rings I have, but I also know how many Poisson points I have. Right? The number of Poisson points, number of black points is also obvious. And each Poisson point corresponds to a minimum of one of the rings. So that means I can say something about the number of minima in a random ring in the stationary case. Because if you take the number of rings, you multiply with the number of minima, you get the number of Poisson points. So if I divide the number of Poisson points with the number of rings, especially when t goes to infinity, I should end up with the expected number of minima of the rings. So when I calculate this, Well, here I have 2TEW over L, which is the number of rings. And of course, the number of Poisson points is just L times T. So when you divide, you get a half L squared divided by the expectation of W. And now I remind you of this special property of the squared Poisson. It was that the expectation of W squared equals lambda squared, which is a half L squared. So the expected number of minima in one of these rings equals the expectation of W squared divided by the expectation of W. Now this reminded me of something. There is a distribution linked to W, which exactly has this expectation. I was hoping that someone in the audience would immediately say it. Which distribution would that be? But it's the size biased distribution. If you take the squared Poisson and you size bias it, which means that you multiply the probability of finding k points by k, then you get a new distribution, a distribution which is always bigger than or equal to 1, and it has expectation exactly equal to this value here. Expectation of W squared divided by expectation of W. So maybe that's something relevant. I don't know. So here is the P star, which is the size biased squared Poisson. It has the squared Poisson probabilities times k, and then you need some new renormalization constant, which is something with the Bessel function, whatever. It's not so relevant. So my guess is that in the stationary case, a random ring has this distribution for the number of minima. Well, of course, I didn't believe it just like that. I did a simulation. I simulated for T is 100,000, I think. I found 130,000 rings. And I just calculated the number of minima, and you get this histogram. And then I took this P star distribution, and I calculated the probabilities of 1, 2, 3, etc. And I'm not sure if something will happen, but if you have a very good beamer, you will see some red lines here. And these red lines, they're more or less exactly on top of the black lines. So that's very nice. It kind of shows that my guess must be right. Right? This size biased squared Poisson must be the number of minima of these rings. The only question is, how do we prove it? Okay. Well, let's see. So to prove this, I first need to make a new kind of state space of rings. And what I'm going to do is I'm going to make a Markov process where you have a ring, and then you put it in the cylinder, you find out what is the next ring, and you put it back in your state space. So one ring gives the next ring. So it's not a continuous process anymore. It's a Markov, chain, actually. And I want to find the stationary distribution of this Markov chain of these strange objects, of these rings. So for that, I'm going to have to code these rings in some way. And I will use the original state space I had, which is E. So here's E. And E has X coordinates and Y coordinates. So you got X coordinates here and Y coordinates here. So this configuration has 2 X's and 2 Y's, and they're placed here in 0L. And then my path is encoded as follows. I go up to the first X, to the first Y, then to the left, to the first X, up, left, up, and to the right. And I end up in the same point, LL. Oh, sorry, which is, because of it's a circle, you get it's 0, 0. That's the idea. And then to place this in the cylinder, I rotate it 45 degrees. So I rotate the picture and I get this path in the cylinder, like that. Yeah, so I have my state space, and I have a way to put this into the cylinder where the left corner is always put at 0, 0, which is this one. Okay, so let's introduce some notation. We have a path, sigma. It has 3 features. It has the number of minima of the path. That's at least one. A path has at least one minimum. But it can be more. And then if it has more than one minima, then it has sigma n minus 1 x's and y's. Those were the positive and negative particles, but now they mean something else. Now, so you have x coordinates and y coordinates, but you only need them if there's at least 2 minima. Because if there's only one minimum, it just means that you go up to the corner and then to the right, and you don't need any x or y's. Okay. And then I map this sigma in E, I map it to the cylinder. And the minima, so these points here, oh, sorry about that. These points, this is a minimum, this one and this one, so this one has 3 minima. These points can be found using the x and y coordinates of the sigma in the following way. So the location of pi is a half, and then this combination of the sigmas. And it's important to realize that this map has a Jacobian, and the Jacobian is equal to 2 to the minus sigma n minus 1. And that's due to this, well, this matrix has a determinant, it's equal to a half. And then you have sigma n minus 1 copies of that, which is why you get this power. Okay, so phi maps sigma into the cylinder. And then we need this Markov chain. So what do? Okay, we start with sigma, we map it into the cylinder, and you get this red path here, which you call R0. And then I create the Poisson process above this path, above the red path. So here I've drawn 2, and I continue to find Poisson points until the new Poisson point is above one of the points I already found. So at first I find this one, and then I start making this path, and then I find this one, and then I start making that path, and then the path closes, and that's it. Then you get the new ring, R1. And this ring has to be translated back to our state space E. And then something interesting happens, because in order to do that, we have to choose which minimum ends up in the origin. So what I do is I make a random map phi star. The random map chooses one of the minima at random, for example, this one. Then I translate this point to 0, 0, and I apply phi inverse. So you take a random minimum, make sure that's in the origin, and then you make this coding with the x and the y coordinates. And that's what phi star does. And this defines a Markov chain. You start with an element in E, and you end up with a new element in E. That's our Markov chain, and I want to see what is the stationary distribution of that. So for that, what I will do is I will write up the transition kernel. The transition kernel, starting in sigma, what is the likelihood of ending up in tau? K sigma tau. And of course, when you integrate this with respect to tau, you have to get 1. And this is a transition kernel with respect to the dominating measure, nu. Okay, so this is complicated. It's not very deep, but you have to be very careful. You have to make sure you get all the factors right, and you have to kind of introduce this notation in order to write down this transition kernel. And that's what we're going to do in the next block. So we consider the cylinder, and we have 2 rings, R0 and R1. And in principle, R0 is below the new ring R1. And I define A of R0 and R1 as the area between the 2 paths. So here's R0, here's R1. There's a certain area in between, and the size of this area is called A. Now, if R0 is not completely below R1, then I call the area plus infinity, which is a little bit counterintuitive, but plus infinity means that e to the minus this thing is 0. So that's important. So that doesn't count. You know, you want R1 above R0 and not crossing or below. That's why we have this definition that it's plus infinity. Now, I fix R0 and I'm interested, what is the density of this new R1? Okay, what is, for example, the probability that I will end up near Q, some ring Q with R1? So I fix a ring Q and I have n minima and I move these minima around a little bit. So I have little blocks around these minima, these n minima. And I'm wondering, what is the probability of my new ring R1 being close to this Q, within these blocks around the minima? Well, how can I do this? So here, this blue one is the Q, and the black ones, that's where the Poisson points have to be. Right? So what I need to do is I need to get 2 Poisson points, one in this block, one in that block. And furthermore, I need this area between, I need it to be empty. Now, if that is the case, then the new path will be the blue one. And if and only if. So if and only if this area is empty and we have 2 Poisson points in these places, then you get the new ring Q. So that's what it says here. The probability of finding R1 near Q equals, you have to have an empty space between R0 and Q, that's e to the minus this A, and then you have to have a Poisson process. Well, it's intensity 1, this Poisson process, so you have to have a Poisson process within dx1, dy1, dx2, dy2, etc., and that has this probability. Okay, so this is how you find a new ring. So this helps us in making the transition kernel, right? Because now I fix sigma in our state space E. I take R0 to be phi of sigma, so I place the ring inside the cylinder. And then I'm wondering, what is the probability that phi star of R1 will be close to some tau? I also fix tau in the state space. And that's where I want to end up with my phi star of R1. So how can this happen? Okay. First of all, I take phi of tau, which is a ring that starts in 0, and then I translate it with xt above, so that it ends up above R0. It can be anywhere above, right? And any location is okay, because if the ring R1 ends up in that location, then phi star will make sure that I find my tau, almost. I will come back to this. Now, so it doesn't matter where this new ring is, as long as it has the correct shape. So that's why I translate phi of tau, and I look at the probability that my R1 ends up in this translated version of phi tau. So that's e to the minus A of that thing. And then, well, I get the size of the box, but remember the Jacobian, so the size in the state space is different from the size in the cylinder. And you get this Jacobian 1/2 to the power tau n minus 1. So that's this factor. And then there's one last factor, which is this one, 1 over tau of n. And what does that mean? So with phi of tau, I made sure I got the right shape. It's the correct shape of the ring. But to find tau back in the state space, I also need to pick the correct minimum, because there's exactly one minimum that gets mapped to the origin. And I need to pick that minimum. And since there are tau n minima, the probability of picking the correct one is 1 over tau n, which is this factor here. Okay, so that's it. That's the probability given sigma of finding tau back. And since this is the probability, I can now write up what is the kernel density, the transition kernel, because I take this probability and I make sure that, you know, it's a density with respect to nu, and nu had these factors n factorial squared and L squared. So I have to cancel them out. So those are these factors here. That's because it has to be a density with respect to nu. And you get these factors. And well, it turns out that this 1/2 L squared, that's exactly lambda. So I can write the transition kernel in terms of this lambda. So going from sigma to tau, you get this nice integral, this factor 1 over tau, and then this factor here with the lambda to the 2 tau n minus 1 and tau n minus 1 factorial squared. That's cool. That's the transition kernel of this Markov chain that I have now. Markov chain of rings. Okay, how do I prove that my guess for the stationary distribution is actually correct? And what I'm going to do is I'm going to kind of use detailed balance, the kind of detailed balance using a reversed process. So I will explain what I mean. So suppose sigma is distributed according to some f, with f a density with respect to the dominating measure nu. Now, if I can find a function k star with the following probabilities, properties, the integral of k star sigma tau nu d tau is 1. This just says that k star is a transition kernel. It's a transition kernel, it's the probability starting with sigma to end up in tau, or rather the likelihood ending up in tau for some process. We're not sure yet which one. But the fact that this integral equals to 1 ensures that that k star is a transition kernel. And then here I enforce some kind of detailed balance. So going from sigma to tau times f sigma in the original transition kernel k must be the same as going from tau to sigma in the new transition kernel k star times f of tau. So from sigma to tau times f sigma, and from tau to sigma times f tau. They have to be equal. So you go back and forth, in fact. That's the idea. And it has to be the same. If you have this, then little f is a stationary measure for k. And in fact, also for k star. So if I can prove this for my guess for f, then I'm done. Then I have the stationary measure. And of course, I need to find a good k star to do this. But, you know, it will be relatively obvious what we should choose for k star. Now, the fact that this is enough is not very hard. What you can do is you can integrate the left-hand side with respect to mu d sigma. And then what you see is you get the likelihood of ending up in tau. So you start with something distributed with f. What is the likelihood of ending up in tau? That's exactly this integral over sigma. But if you integrate the right-hand side over sigma, well, with property 1, you get f of tau. So indeed, the likelihood of finding tau is again f of tau, making f the stationary distribution. Okay. And my guess for f, of course, is, well, I already said it. What I will take is I will just take p star of lambda at sigma n. So I make sure that the probability that you find n minima equals this size biased squared Poisson distribution, this p star. That's what I do by taking f sigma equal to this. Okay, all I have to do now is choose k star. Well, as I said, k star is like a going back, so it's like a reversed process. So what I do is, let's go back to the picture, this picture here. So here the bottom one is sigma, and the top one is tau. And with k star, I now start with tau. I start with the top part, and then I go down until I find Poisson points. And these Poisson points will be the tops of the sigma. So it will be the maxima. And once I find these 3 points, then the path is fixed. Now, this is very similar to the way we did when we go up, right? It's the same process, basically. There is a slight difference because I now find the maxima instead of the minima of the top. So what I have to show is that if you encode the way we did with the minima, but you look at the maxima, then the Jacobian of this map has to be the same as the one for the minima. And it's not hard to check this, but you have to check it's the same Jacobian. And once you've done that, you get the following transition kernel. This one, it's basically the same as before, but there's a slight difference. So I now fix phi of tau, and then I have to move phi of sigma, I have to move it down so that it gets below phi of tau. So that's why I subtract x of t here. But of course, if you take two paths and you move one down, the area is the same as moving the other one up. It's the same thing. You get the same area in between. So I kind of transform this integral by moving the whole thing up, and I just realized that this factor is the same factor as we had before. It's the same thing. And this is, of course, very relevant. This is why it works. So we don't have to calculate this area or do any complicated thing. We just have to note that the reverse process has the same area between these two paths, sigma and tau. Now, of course, the factors here, they're different, because before they were factors with tau, and now they're the same factors with sigma. And, well, I rewrite them a little bit. I get 1 over sigma, and here is sigma n minus 1 factorial. I rewrite it into sigma n factorial, and then instead of 1 over sigma, I get times sigma. And the reason why I do this is the following. If I now want to check this detailed balance formula, what I do is I take k of sigma tau, and I divide by k star of tau sigma. So I divide these two things. And I note that if you look at k star tau sigma, this thing here, well, it's exactly the p star. It's exactly the size biased distribution of lambda, because you get the lambda squared to the power sigma n, you get sigma n factorial squared, and you get the extra factor, the size bias factor, sigma n. So what it says here is just p star of lambda sigma n, this factor here. And in the same way in the top, you get p star of lambda tau n. And then there's this extra factor lambda minus squared, but well, lambda minus 2, it cancels. And of course, p star lambda sigma n is exactly f sigma, and here you get f tau, proving the detailed balance, and therefore proving the distribution of our Markov chain. So in this picture, this one, we now know what is the distribution on a horizontal line, what is the distribution of the green points, but we also know the distribution of the rings themselves. What do they look like? We know what is the distribution of these things. These are all the results we have so far. What I'm hoping is that this might give us some insight in, for example, what is the variance in the number of rings? If we have an exact formula for that, and we rescale it by L going to infinity, we should find the cube root scaling. And if we know a little bit more, we might also find a Tracy Widom and maybe some other interesting aspects of the infinite case. But also, the fact that we have these exact formulas might help us in maybe also finding new determinantal things or something like that. Anyway, I thought it was fascinating that we were able to describe the whole shape of the path in this process. And well, I hope you agree with me. Thank you very much for your attention.
Martin?
Hi, Martin.
Thank you very much. Hi, Eric. Thanks for your last talk. I have 3 questions, actually. The
Okay.
first, how is this model different from something called the polynuclear growth model, which was one of the first integrable particle systems by Herbert Spohn, Michael?
Remind me?
Ferrari.
I think it worked.
Honeycomb, yeah. Polynuclear.
Yeah. It worked, I think, but
Is this better? Yeah, I think. So polynuclear growth model, it's called. And I've seen it first from Michael Preyhofer and Herbert Spohn in 2002, I believe, or so.
Right.
And it seems to be a very similar model. And they do all the integrable stuff there. So GOE limits and trace rhythm distributions and everything. I don't know if it's connected. I think
But it's not periodic.
Sorry?
It's not periodic.
No, it's not periodic. No, they do it on the infinite volume. Yeah.
So is it different from the Hammersley process, you think?
Sorry?
Is it different from the Hammersley process? Is it not just the 45-degree Hammersley process, this polynuclear growth?
Yeah, I think it's very similar to the Hammersley process. Yeah.
Yeah, I would also think so.
Okay, so your main difference is that you do it in the periodic case.
Yeah, so the idea is that, so as I said, the motivation from Pablo was a little bit different. He had this periodic case and he wanted to see, what can we say about this? And then we realized this connection to the non-periodic case, and a little bit surprising that the periodic case is also exactly solvable. And in a way, this is, I would say this is stronger, since the infinite case is the limit of this case.
I see. Okay, because my two other questions would be how to get rid of the periodicity condition, but I'm not sure if I want to ask those.
But you see, if you get rid of the periodicity condition, you just get the rotated Hammersley process that I described. You just get the same thing.
Yeah.
And maybe I didn't mention, but also in the Hammersley process, and this is also not written down, but I know it's true, these paths, you get these infinite paths, once you rotated it, they're a little bit horizontal. These can also be described by an exponential jump to the top right, and then an exponential jump to the bottom left, an exponential to the top right, etc. So it's like a random walk. And this would also follow from this periodic result.
Okay, thank you. That puts things in perspective. So essentially, you just restricted this Hammersley process into a periodic thing and examine what
in a specific way. And then it turns out it's still solvable, which is not obvious, I think.
Okay, thank you.
Any other questions for Eric? Now let's thank Eric again.